Today we're talking about exploring network programming by building a Toxiproxy clone. So my name is Jordan Neufeld, and I do work at Shopify. So the meme that we use internally is Spotify, Shopify, same thing. But anyway, I am a site reliability engineer at Shopify. We focus on resiliency, incident response, a little bit of scale testing, assisting with retrospectives, things like that. I call myself a self-taught gopher. My career experience, my formal training is in network administration, things like how to restart Windows servers, all that fun stuff. But in my career, up until this point, most of my time has been spent debugging Linux, working with Kubernetes, and fighting with distributed systems, those kind of fun things. So I mentioned that I'm a self-taught gopher. So in my early career, I started teaching myself JavaScript and Node.js for programming, and as you might imagine, that was kind of soul-crushing, right? We talk about things like, the NPM stuff and, callbacks, not super fun. So I started exploring Go as I came to it through the Prometheus ecosystem, writing Prometheus exporters and things like that. And the thing that, if I had to choose one thing, it's definitely the type system and how that can reduce this cognitive overhead, right? We don't have to guess when I'm in my editor what the inputs or outputs of functions are going to be. So that was really the game changer for me, and I was sold. So on the program, it says it's for everyone. Of course, it's for everyone, but this talk is a little more geared towards beginners and intro-level folks. I still call myself a beginner, even though I've been writing Go for about 3 years. But I like to tell myself that I keep learning through practice, exploration, trial, and error. But if you're not a beginner, you're the expert, definitely stick around and come chat after. I'd love to learn from you as well. So today, what are we doing? We're going to talk about why we would build network tooling in Go. We're going to talk a little bit about Shopify and chaos testing. We'll touch on what Toxiproxy is, and then we'll build our demo Toxiproxy clone. So let's take a step back, though. We need to kind of define what I mean by network tooling. Some of you may be familiar with the OSI model. There's 2 different variations, the 4-layer and the 7-layer. When we talk about the 4-layer here, we're talking about these 4 layers. So at the top, the most high level is the application layer. If you're writing an application that's focused on the application layer, you're going to be writing like a JSON API or something that's rendering responses to web browsers and that type of a thing. The next layer down, a little bit lower than that, is kind of focused on TCP and UDP, so the transport layer. Under that, we have the internet layer. So if you were doing things like building a router where you have to route IP addresses, that's kind of that layer. And then network access is below that, if you're talking about drivers and putting bits on the wire, things like that. Today, though, we're going to be at the transport layer talking about TCP. So why would we do this in Go? Well, we're literally at GopherCon, so there you go. But more seriously, there's a couple key points here. The top of the list here is about cross-compiling portable binaries. In my career so far, I've kind of needed to write some of these experimental network layer programs and need to deploy them, quickly and easily. So using Go for this, we can just copy it to a Linux server and it's going to run, it's going to work. If you were using Python or Node.js for this, you need to make sure that your right version is installed on the server. You need to deal with your dependency management on the remote side. With Go, you don't have any of that. A lot of folks and a lot of talks always reference that the standard library has great support for things, right? And yeah, we say it has batteries included. You might not even need dependencies, as you're going to see in our demo when we're building this TCP tool. And it is easy to get started, as we'll again see in the demo. It's really accessible to solve for custom needs. And when you can kind of step to this lower level of building tools like this, the world really opens up to what you can do, because you're not depending on other folks on GitHub to write tools that fit your custom business needs. So why would you want to build transport layer tools? Let's back up a little bit and talk about why we did it at Shopify. So Shopify is a large e-commerce platform. We have kind of a hybrid architecture. It's a monolith surrounded by a sprinkling of other services. So we do have complex interactions between the monolith and services to services and things like that. When you have this complex system, you want to consider designing for resiliency with resiliency principles in mind. It's important to consider things like failing fast if a service is timing out, failing gracefully if a dependency is unavailable, like your caching service, or if your database is unavailable. You want to know how to handle that gracefully. Also things like limiting the blast radius by designing with isolated components. So designing in this way is great, right? But we need to be able to test these assumptions. So unit tests can test code business logic, but how do we unit test things like a flaky network, right? So in order to do this type of testing, we have a thing called chaos testing, or we call it game days at Shopify, where we test these resiliency assumptions. So in game days, we focus on introducing failure and observing results. We can do this in testing environments, in staging environments, or in production itself if our experiments are controlled enough. We do want to remember, though, like the only substitute for production is production, right? So considering the value that testing in production can give us. So what do these look like, right, these experiments? Practically, one of the ways that we do this is by simulating a slow or down connection between like a web app and its dependencies. So this might be a web app between a MySQL database, or a web app and a cache like Redis, or a web app and a remote HTTP API, for example. So one of the tools that we use in game days to simulate these network connection issues is Toxiproxy. It was written in 2014. It is an open source tool that you can find on GitHub, written in Go, obviously. It is a proxy to simulate slow or down network connections. And as we mentioned before, it operates at the TCP layer. So a common way we would use this is putting Toxiproxy between a web app and a MySQL database, for instance. In terms of what Toxiproxy looks like in the architecture, there's a basic mock-up here. The gray square is the Toxiproxy server itself, i.e. the Go binary. So we have a client on your left here connecting to Toxiproxy listening on a port. Toxiproxy then has this downstream connection. It passes the data to an upstream link, and that upstream link passes it to an upstream connection, which connects to the real dependency, like MySQL in this case. On the way back, it goes the same way through a downstream link back to the client. So I didn't really describe anything interesting here. It's just passing data through. And that's true in its basic setup. The interesting part comes when we add some business logic here. So the business logic that we put in Toxiproxy, you can add these concepts of toxics. And these toxics live on the different links. So you can add a toxic on the upstream link or on the downstream link. And in this example here, we've added a latency toxic on the downstream link. So effectively, the client here has a simulated slow network response coming back from MySQL. So let's touch on a little bit of the Go standard library that we're going to see come up in the demo. This is definitely not an exhaustive tour. It's just exposing you to a few pieces that we're going to see in the demo if you haven't seen them before. So the first thing that we might consider when we're building like a networking tool at this layer is we need a way to read data, like reading data from a TCP connection. One of the things that we're going to see in the demo is an interface called IO Reader, and it looks like this. So this interface is important because we need kind of a generic way to read from a real network connection or read from a link, like the upstream links and downstream links. Same thing with the reader. We're going to want a way to write data to places. So writing a data to a network connection or to the link again. Now, We talk about reading and writing to connections, but what about a connection itself? Well, the connection itself is an interface as well. So we have typecon interface here. This represents a TCP or UDP connection. We can see that it actually does implement IO reader and IO writer on this interface. It actually has more methods as well, close, and a whole bunch more that I haven't listed here. We're only concerned with the reader and writer methods for our demo. So how do we get a connection object? There is a handy function here in package net called dial. So we use it like this. We call dial with a protocol, so TCP in this case, and we give it an address and port to connect to. In this case, it's golang.org, port 80. Once we have this connection object, we can now read or write data to it. Similarly, if you want to receive connections, i.e. like wait and listen for connections to come in from a client, you are going to be using net.listen. And you set up a listener like I've shown here. You call net.listen with TCP4 and provide an address and a port to listen on. So this one is a little bit different than the dial, right? Once we have a listener, we call listener.accept. Your code will block and wait for a client to connect to you when you've called listener.accept. It's kind of like an analogy where you might have a phone number and a phone set up, but you're waiting for someone to call your phone. And accept is actually picking up the call and answering it. The last one that we're going to look at here is io.copy. io.copy can copy from any generic IO reader interface to any generic IO writer interface. So we're going to be using this to copy data between these real network connections and these links. So it's important that we can copy between like generic things with IO copy. So let's take a little bit of a look at the demo here. Okay, so the very first iteration we have here, it's a super basic Go program, and all we're doing here is setting up a listener on port 1337, TCP version 4. Then we're calling listener.accept here, so we're waiting for somebody to connect to us. Once we have accepted that, we now have access to a downstream connection where we can talk to the client. We can read data from the client that they might be sending to us, or we can write data to the client. What we're doing with that connection in this case here at this line is we're just going to be writing some data to the client. We're going to write a byte slice, which just says hi, and then followed by a new line. And after that happens, this program is actually going to terminate. And we do have a defer here of close, so the connection is going to get closed. Let's take a peek at what that looks like. So we will start the server here. Now, because this is just pure TCP, I can't test it with curl or anything just at this time. So we're going to be using netcat to connect to localhost on port 1337. So we can see that we opened the TCP connection successfully, and we have one message from the server. It said hi. So great. Let's try this again. Okay, the second time it did not work. Why is that, right? We get a connection refused here. We look over back at our server, and our server has actually terminated, right? It's not running anymore. What happened here is what I was describing a little bit earlier. After we had accepted this connection from this client, we processed this one connection, and then we were done, right? This was kind of the end of the server here. That's not really typically how we write proxies and servers, right? So let's improve this a little bit. Okay. So in the next kind of version here, we have a for loop that we've introduced. So we're setting up a for loop that is basically an infinite for loop. When we enter into that, we're going to accept one connection that's coming in here. Now we have access to this downstream connection from this client, but we need to actually deal with this in some way. Because we want to be able to accept multiple connections from multiple clients all concurrently, we need to spin up a dedicated Go routine now to handle this connection. So that's what we're doing here in this block. So we're doing gofunc, we're passing this downstream connection in here, and then we're handling it in much the same way. We're just writing hi to this client back, and then the connection is getting closed. So this should be able to handle multiple connections this time. Let's try it out. You'll try it again, and it worked the first time. We do it again and again. Great. So now we're one step further in being able to accept connections from multiple clients, and our server has not, it has not exited, right? It's still going. So right now, all we're doing is accepting a connection from a client and responding to it and closing it. We're not even doing a dynamic response, right? It's just super basic and static. That's not very interesting. Let's make it a little more interesting. The next version here, we're actually implementing a bit of a proxy itself, a raw TCP proxy. So what's different here is that when we have this Go routine to deal with this connection, we are actually connecting somewhere else from Toxiproxy. We're doing an additional net.dial here. So we're making another outbound connection. And you might ask, like, well, where are we connecting to? I have a different echo server that echoes hello world over HTTP running on my local machine here. That's running at localhost port 8080. So what's going to happen now is we're going to start up our Toxiproxy proxy here. We're going to accept a connection from a client. We're going to proxy this to our other upstream HTTP server, and we're going to proxy the response back to the client. So at this point here, we have two connections in our hand. We have our client and our server, and we're sitting between them. So we still need to do something to connect these two pieces together. So in order to connect these two pieces together, we are going to make use of IO copy that we saw a little bit earlier. So we are doing IO copy here. We're copying data from our downstream connection to our upstream connection. And we actually have to copy the responses back from our upstream connection to our downstream connection. So we need to copy the requests one way and the responses back the other way. You might actually notice here that we do launch this first IO copy in its own Go routine. That is because we want to be able to have this one executing and running in the background, and we want to move on to this one and execute this code as well so that we can read the responses coming back. Let's see if this works. So I will run the server again. Now, because I have a real HTTP server that we're proxying to, I can test with something like curl and see if we get our HTTP responses back. So let's curl the proxy. Okay, and I get back hello world. Great. I'm using time here so that we can just prove that, yep, it came back quickly, and later on in the demo we'll see that it doesn't come back so quickly as we want it to. So, great. We have a proxy now that's just proxying TCP. It could proxy other type of traffic too. Right now it's proxying the HTTP over this TCP. But we don't have any business logic in here yet. It's pretty boring, honestly. Like, it doesn't do anything fun. Let's make it do something more fun. In order to do that, we're going to need a way to kind of intercept these, this stream of bytes from the source to the destination and the other way around. So just like we saw in the mock-up diagram that I had, where there are these two concepts of links between the two connections, that's what we're building in here next. So we have a type called link. And in this type here, we just have a channel, and it is a channel that has a byte slice that goes over it. Now, this link needs to kind of operate kind of like a network connection, but more specifically, it needs to implement IO reader and IO writer so that we can make use of IO copy to copy data between a connection and a link, or a link to a connection. So that's what we are doing here. This function is implementing IO reader on this link. So basically, it reads from an underlying channel and then copies the data to the byte slice here and returns the number of bytes that it copied. In the write implementation, it's implementing IO writer, so we know how to write data to a link. And in this case, it is taking in a slice of bytes and sending it to the channel, and then returning the number of bytes that we sent. Okay, so we have the definition of what a link kind of looks like. We don't have any links built yet in the program. If we come up here, we see that we are building links right here and right here, one for upstream and one for downstream. Do note that this is now one upstream link per incoming connection and one downstream link per incoming connection. So we are still inside the one Go routine that is handling this incoming connection. So just to review, we have a client connecting to us. When that happens, we accept the connection, we spin up two different links, and we make another connection to an upstream server. And we're now juggling all of these things, all of these pieces. So in order to connect all of the pieces now, we have these 4 different endpoints, right? We have to do some more IO copying to copy data. Now first, between the downstream connection to the upstream link, so this is the real client, my curl client, to the abstraction, which is the link, and then from the upstream link to the upstream connection, which is the real server, and then also have to copy the responses back down as well. So there's no additional business logic yet here exactly, but we're setting up to be able to inject business logic into here via the links. So let's make sure this still works. We'll do go run. And we will do our curl again. Okay, nothing magical happened. It still said we got our hello world response from our upstream server, and it's working great. Let's now do something more interesting, and we can actually start to put some more business logic in there. Okay. Now, this variation, it gets a little closer to what Toxiproxy is doing, and we'll actually see that we do have some latency now when we're able to test this version. So how are we injecting this latency? Let's take a look. In our link definition now, I've updated it to include a field called latency, which is of type time.duration. So we can accept a duration there like 1 second or 10 milliseconds, anything like that. And in this example here, I've chosen to implement the latency on the read function here of the links. So we are reading data from the channel, and then we are doing a time.sleep. We're doing a time.sleep for however long the link said here in our, however much latency was defined on this link object itself. In the real world, you could do more fun things like adding jitter and etc. on these sleep latencies. And that's certainly some of what Toxiproxy itself can do. For this demo, it's just a static amount of latency. So we're doing some sleep here, and then after we pass the sleep, we're actually doing our data copying, and then we return. So let's take a look at how the link definitions change in this case. Now, when we're building our links here, we have the ability to inject our definitions for how much latency we want to add. In this case, I just chose time.second here to make a good example. So we can have 1 second of latency on our upstream link and 1 second of latency on our downstream link. In Toxiproxy, the tool itself, you can choose to put latency on an upstream link or on a downstream link or both of them at the same time if you wish. So before we launch the program, let's take a little bit of a closer peek on where that latency is actually happening, which one of these copies, right? We remember down here that we implemented the latency on the reader function on the link itself. So where does that happen? We need to look for instances where we're having that read function called from on our links. So that's going to be here, this line that's highlighted, and this line. So when we are reading from our upstream link to copy it to the upstream connection, that is where we're going to have some introduced latency. And on the way back down, when we are reading from our downstream link to our downstream connection. So on the way back to the client, that's going to have latency as well. Okay, let's see what this looks like in practice. So I'm doing the time curl again here so we can see how long it takes. Responding a little slower, as we might expect. Okay, and we do have 2 seconds of latency now. So that's pretty much what we expect here in this case. So we have 1 second being added on the way up to the curl, to the server itself, and 1 second being added on the way back down to the client. So let's talk a little bit more about these copy routines. This is a demo program, but we can do a little better, right? We might recognize that IO copy here has the potential to return an error, and we are just launching these Go routines, into space and hoping that they exit maybe sometime, or maybe they'll throw an error and maybe not. We actually have no idea in this case. This is fine for, it's fine for testing, but we really kind of want to know what's happening with our Go routines because we don't want them to be leaking, right? If these were leaking, they would stack up and use memory and resources, and our server might eventually crash. Not great. Let's see if we can prove what's happening to these Go routines. In this next iteration, I have a helper function called copy and log. It is basically doing the same thing that IO's copy is doing, but we are just logging how much data we're copying between these two different places, and we are logging any errors that we get from IO copy. So the signature is much the same here. We have a destination IO writer, and we just have a label for this destination to make it easier to log. And we have a source IO reader and a source label as well. The magic here is still happening by IO copy, right? We're copying from a source to a destination, and we have an error that might be encountered, and we have a number of bytes that is copied. You'll notice here that if we encounter an error, we are going to log out this error to the console, but we are actually not going to return there. This error might be encountered after we have actually successfully copied some amount of bytes. So we do still want to hit this logline message that tells us that we did copy this many bytes from this source to this destination. So even though errors might be encountered here in IO copy, it doesn't necessarily mean that it's a fatal error and that we have to return. And we do still want to log both messages. So in this example here, if we do see a log message that says copied X bytes from source to destination, if we see that, we know that this IO copy must have completed because we got to this line, and therefore these Go routines here must have completed. So that means that they're no longer leaking, which is great. We don't want leaking Go routines. So the only other change here, instead of running go io.copy, I'm just running my copy and log, basically a wrapper helper here. Let's see what this looks like. So I'll do go run. Doing another curl. Okay. So I'll stop the server there. We only got one log message, right? We only got copied 78 bytes from downstream connection to upstream link. That's not really what we were expecting, right? We talked about if we were terminating these goroutines all cleanly, we should have received 4 different logline messages. So we might have a problem here that we need to deal with in order to make this program a little more efficient. Let's look at which one we actually got. We copied 78 bytes from downstream connection to upstream link, but that's the only one that ever logged. Let's look at why that might have been. So it was downstream connection to upstream link. So that's from our initial client connection to the upstream middleware. That very first part of the journey. That's the only one that finished. If we look at the docs here for IO copy, it says that it copies from the source to the destination until either end of file is reached on source or an error occurs. Well, as it turns out, when I am doing my curl, curl is not maintaining that connection open, right? So curl is actually closing this connection when it's done. And that kind of signals to IO copy that yep, we're done here, so it has a chance to exit. And therefore we get the log message for this one. But that's not actually the case for these other goroutines. And they're a little bit special about why they don't exit in the same way. For upstream link here, this one is one of our kind of custom things, like our custom link implementation. We haven't told it how to deal with closing of connections or anything else that might be happening. So io.copy is still just trying to copy data from the link to the upstream channel. It's just still trying to do it, It's never completing. The other ones that are still hanging out there is this one down here. So the downstream link, that's the other side of the link as well, right? We haven't told our link when it's done copying data. It's just still trying to copy. IO copy is still trying to just see if there's more data on that link, but there is no more data on that link. This one in the middle that I've highlighted is interesting, right? This one is actually from our upstream server connection itself to our downstream link. So our HTTP server, that is our dependency in this case, it didn't close any connection when it was done sending the response back to Toxiproxy. That's very interesting, right? If I would have actually left the server running for a little longer, we might have seen it close it, but the Go server that is the dependency in the back end here, it is trying to be efficient and not necessarily closing the connection after it has sent its first HTTP response, right? It's keeping that open for a little bit to see if any more data is going to be sent down that connection. So we've identified that we have a problem here, but we still have the problem. We haven't fixed it, right? We're just logging that. Yep, we do have a problem. Let's see what we can do to correct this. So when you're building a network kind of tool like TCP proxy or any HTTP proxy, there's always going to be several ways to handle things like this, right? There's, tools like Envoy, there's 1,000,001 knobs with timeouts and things to tweak. I've taken the approach here to kind of add some timeouts to try and close up these goroutines that are just kind of hanging around after a certain amount of time so that we can be sure that they do exit eventually. So I have a const up here called IO timeout, and just 10-second timeout, just because we don't want to wait around forever here. And what I'm doing here is not quite perfect. It's good enough for the demo, but it's not a production implementation by any means. What we're doing here is saying we're setting up a deadline. So when we have this connection from our client, we want to store a variable that says 10 seconds from now, that is our deadline. So we're going to mark each of our downstream connection and upstream connection with this deadline, with the set deadline function here. And when that happens, those connections are going to get closed up when we hit that deadline. So I mentioned this isn't production implementation. That is because in the real world, you might have like a persistent connection from an HTTP client to Toxiproxy or a MySQL client to Toxiproxy. If we just do this deadline approach, we might be closing that connection when the client is trying to send more data over the wire. It's not a production way to handle it, but it's good enough for our demo here to prove that this is one way-ish to kind of get around it. So that works for our real TCP connections here. What about our links? Our links are special kind of manufactured things, right? They're not really a connection. They do implement IO reader and IO writer that are kind of emulate some pieces of a connection. So for our links here, I'm kind of adopting a little bit of in the middle of a strategy. I have a select block here. And the first case statement is try and read data from this channel. And if there is data on this channel, great. Let's do our same kind of business logic flow. We'll do our sleep, and then we'll copy some data, and we'll return out of there. Great, that's perfect. But the other case here is a timer that will fire after a 10-second IO timeout. So if we enter this select block, that is to say, if read was called, but there's actually no more data on this channel for the link to read, we will hit this case statement here. So this timer is going to fire, and then we enter this piece of code where we say, okay, I didn't read any bytes here. I read 0 bytes. Now I am going to return an io.eof, an error basically. That io.eof might sound a bit familiar, right? If we come back and look at io.copy, io.copy copies until there's an EOF error. Until EOF is reached on source or an error occurs. So by us returning this special io.eof error here, we are signaling to io.copy that like, yes, I am done. And then when io.copy is actually done, we will move on and progress past this code block, and we will hit our final line that says copied X bytes from source to destination. So we do have these two timeouts in these two places now, and let's see if this is going to work. So before we run this though, let's talk about what we might expect to happen here, right? We have a client that is connecting to Toxiproxy, and Toxiproxy is sending it to a link, and there's a little bit of latency there after it sends it to the link to the upstream, and then it's sending the capturing the responses from the upstream back to this link and back to the client. And we want to be able to see these 4 different log messages that say, I copied data from these 4 different places. If we see these log messages, we can assume, and we kind of know by this proof here, that those IO copy goroutines are done and we have cleaned up successfully. So let's run the server. We'll use our time curl again. Okay, 2 seconds, cool. We come back here. We're still waiting for our 10-second timeout. Look at that, magic. So we do see 4 different of these copied log messages. So we see copied from downstream link to downstream con to upstream link, and then upstream con to downstream link, and all the 4 that we were expecting. Perfect. So that means that these 4 different copy routines have successfully exited, and we're not leaking these goroutines anymore. But you might have noticed this one up here. We do have an error that pops up. This error is getting logged from our new copy and log function, right? This one says error copying from upstream connection to downstream link. And it says there was an IO timeout. That's very interesting. This one is from the upstream connection, so our server, to our downstream link. So it's the response coming from our server to our middleware. That piece kind of broke here with an IO timeout. That IO timeout is happening because we set this deadline here, and we effectively told it to IO timeout. So this one gets it gets an error thrown, but in this case, it's not a fatal error by any means. We had already copied all of our data, and yeah. Okay, so now we have seen a basic, super basic example of like how to put some latency in between a curl client and a web server with this very basic Toxiproxy clone. Okay, let's go back over here. So to recap about what we did today here, building this was pretty productive, right? We didn't have to do anything super fancy. The whole source code here that we saw today was like 80 some lines. Of course, it wasn't 100% production ready, but it's pretty close. I mean, like it doesn't have logging, monitoring, and all of that other magic. But in a pinch, it'll do it'll get the job done, and it'll get you productive. It is accessible to use Go to build tooling like this, right? As we saw, there's great documentation. These pieces that are provided by the standard library are super easy to use and like relatively easy to work with and understand. And I had fun building this demo. I hope you had some fun watching it. And yeah, that's all for my talk. Thank you very much for coming.